Welcome to the deep dive. Today we are jumping into a brand new framework for large language models. It's called Dynamic Large Concept Models, or DLCM.
Yep. And this is a big one. It's a major collaboration with folks from ByteDance Seed, University of Manchester. And it really challenges how LLMs think.
So what's the core problem they're tackling here?
Well, the thing is, traditional LLMs treat every single token, every word, uniformly.
The same amount of compute for everything.
Exactly. But, information density in real language is all over the place. Think about it. You don't give the word the same mental energy as a critical phrase in a contract.
Right. So current models are just burning capacity on predictable text and I guess under allocating it where the real semantic heavy lifting is happening.
That's the waste DLCM is designed to fix.
Yeah.
It learns these variable length semantic concepts right from the latent space.
So it groups words together.
It does the heavy reasoning on those groups in that compressed space, and the results are pretty significant. We're talking an average performance boost of plus 2.69% under matched inference FLOPs.
Okay, so same processing power, better results. It all comes down to that smarter focus.
It does. The core idea is this dynamic segmentation. DLCM breaks the input sequence into these concepts, and they aim for an average of about 4 tokens per concept.
Why 4? Is that just an arbitrary number?
Not at all. They found it was the sweet spot, really. A good balance between efficiency and making sure the model stays stable.
Okay, let's get into the pipeline. How does the model know where one concept ends and the next one, begins? It almost sounds like it needs to hit a mental spacebar at just the right time.
That's a perfect way to put it. And it happens in 4 stages. First, a really lightweight encoder gets the initial token representations.
Okay.
Then comes stage 2, the critical part. Dynamic segmentation. It looks at the local dissimilarity between adjacent tokens.
Using cosine similarity, right?
Exactly. So if the meaning suddenly shifts, the model detects that boundary and says, okay, new concept starts here.
And once you have these concepts, these chunks, the reasoning has to be really robust to handle any information loss from that compression.
Absolutely. Which brings us to stage 3, concept-level reasoning. This is where a massive, high-capacity transformer takes over, but it only operates on that compressed sequence of concepts.
So that's where the deep thinking happens.
That's where it happens. And finally, stage 4 is token-level decoding. It reconstructs the final predictions using cross-attention, looking back at those high-level concepts to guide the output.
It sounds like you have 2 completely different transformers working together, a small one for tokens and a huge one for concepts. Training that setup must be a nightmare.
Oh, it is, or it would be. They needed a pretty advanced trick to get this heterogeneous architecture to play nice.
What did they use?
It's called decoupled maximal update parametrization, or EP. Basically, they had to scale the learning rates inversely to how wide the different components were. It was essential for stable training.
And what about managing the compression itself? I mean, code compresses very differently than, say, technical English. How do you stop it from just going haywire?
That's where something called the global parser comes in. It's a regularization mechanism that balances the compression ratio across the entire batch, not just one sequence. So it allows for that content-adaptive compression while keeping it all in check.
This brings us to what you called the capacity swap. DLCM has more parameters, right? 2.3 billion versus a 1.3 billion baseline.
It does, but because that deep reasoning backbone is working on a sequence that's 4 times shorter, the effective compute, the FLOPs per step, stays about the same.
So they're just reallocating the power.
They've shifted about 1/3 of the inference compute into that smarter, higher capacity reasoning part of the model. And it pays off.
Especially on reasoning tasks.
Big time. You see gains like plus 3% on OpenBook QA.
Hmm?
But what's really fascinating is the analysis they did, which shows this U-shaped loss profile.
So this is the trade-off. It's sacrificing a little bit of precision inside the concepts.
Precisely. The model gets much better. The loss drops significantly, right at the semantic boundaries, at the start and end of concepts. But it might have a tiny bit of degradation in the middle. It's trading token-level perfection for a much better global understanding.
And from an engineering perspective, they also found a way to speed up the decoder's cross-attention, which sounds messy.
Yeah, that irregular attention pattern could be a bottleneck.
Mm.
But they use a trick called concept replication, which lets them use highly optimized kernels like flash attention. It gives them a speed up of up to 1.73x, especially on really long sequences.
So if we pull all this together, the big takeaway seems to be that scaling LLMs isn't just about more parameters or more data anymore.
It's about rethinking where you actually perform the computation, shifting it towards this kind of concept-level reasoning.
It really feels like the next logical step.
A new paradigm, maybe.
Now, the sources did note that while it's great at reasoning, DLCM can struggle a bit with tasks that need super fine-grained understanding, like bool Q. It showed a small dip there.
Right, that trade-off we mentioned.
So it makes you wonder, if a future model could adaptively select its granularity, if it could operate at the token level for tiny details when needed, and then switch to the concept level for high-level reasoning, what kind of problems could that model finally solve? Something to think about until our next deep dive.